Have you ever wondered if time travel could be more than just science fiction? From H.G. Wells' The Time Machine to the DeLorean and Back to the Future, the concept of time travel has permeated pop culture like a constant, tantalizing thread. It's a concept that has captured our collective imagination, beckoning us with the allure of the unknown and the thrill of the impossible. We humans are a curious lot. We've always been fascinated by the idea of bending the linear flow of time, of leapfrogging from one era to another, or even reversing the course of events. We dream of visiting the past to witness history unfold, or of peeking into the future to see what it holds. The idea of slipping through the cracks of time has been the cornerstone of countless stories, movies, and theories. But is time travel merely a figment of our collective imagination, or could it be a scientific possibility? Let's delve into this intriguing question as we journey through the annals of time. To understand time travel, we must first understand what time is. Picture time like a river. It starts at the source, which we can think of as the past. It flows towards the ocean, which in our analogy represents the future. We're all on this river, carried along by the current, moving from the past and into the future. This is how we commonly perceive time, a one-way journey from yesterday to tomorrow. But here's where it gets interesting. Physics doesn't see time this way. In physics, time is considered a dimension, just like length, width, and height. Imagine you're in a room. You can move forward and backward, left and right, up and down. You're free to move in any direction within these three dimensions. But what about time? Well, in our everyday experience, we seem to be stuck moving in just one direction, forward. We're always inching from the past, through the present, and into the future. But physics, particularly the study of space-time, suggests that time is just another dimension we exist in. So theoretically, it should be possible to move forward and backward in time, just as we can in space. However, there's a catch. While we have a lot of freedom to move in the dimensions of space, our movement in the time dimension is heavily regulated by the laws of physics. These laws, as we currently understand them, seem to insist that we can only move forward in time, never backward. But this doesn't mean time travel is impossible. If anything, it simply means we haven't yet figured out how to do it. The theories and equations of physics hint at the possibility, even if they don't yet provide a practical guide for how to achieve it. So if we can move forward and backward in the other dimensions, could we do the same with time? This is the question that lies at the heart of time travel, and the answer could change our understanding of reality itself. Enter the world of Albert Einstein and his theory of relativity. Let's imagine you're sitting on a train. Now, this isn't just any train, but a super-fast, hyper-speed train that can move close to the speed of light. You're sitting there, reading a book, sipping your coffee, and to you, time seems to be moving as it always does, second by second. But here's where Einstein's theory of relativity comes in. As your train speeds up, something peculiar happens. To an outside observer standing on a platform, it would seem like your train and everything inside it, including you, is moving in slow motion. Your coffee doesn't cool as fast, your page flips are in slow motion, even the ticking of your wristwatch slows down. This is the essence of Einstein's special theory of relativity, which essentially says that time is not absolute but relative. It depends on how fast you're moving and how much gravity is pulling on you. Now let's take our train scenario a step further. What if this train could somehow reach the speed of light? According to Einstein, time would stand still. Your coffee would never cool, your book would be forever on the same page, and your watch would stop ticking. But remember, this is from the perspective of the observer on the platform. For you, inside the train, time would seem to pass as usual. This is a simplified version, of course. The real theory involves a lot of complex mathematics and the concept of space-time, a four-dimensional fabric of the universe that gets warped and twisted by mass and energy. Einstein's general theory of relativity, the sequel to his special theory, even implies that if you could somehow bend this space-time fabric enough, you could create shortcuts, or wormholes, through space and time. Einstein's theory suggests that time travel might be possible, but only into the future. But remember, this is all theoretical. As far as we know, no one has yet built a train that can reach the speed of light. But who knows what the future holds? But what about traveling to the past? This is where wormholes and time machines come into play. Wormholes, in essence, are shortcuts through the fabric of space-time. Picture a sheet of paper representing our universe. Now fold that paper until 2 points touch. The direct line that connects these 2 points, bypassing the surface of the paper, is a wormhole. In the context of time, if one end of the wormhole is in a different time than the other, voila, you've got a potential path for time travel. However, don't pack your bags for the Jurassic era just yet. While the math of Einstein's theory of relativity allows for the existence of wormholes, we have yet to actually find one. Moreover, even if we did, they are predicted to be incredibly unstable, collapsing instantly unless some form of exotic matter with negative energy density can be used to keep them open. And this exotic matter is, for now, purely theoretical. Now let's venture into the realm of time machines. The concept of a time machine is almost as old as time itself, but is there any scientific basis for them? Surprisingly, yes, some solutions of general relativity do allow for the possibility of time machines, such as the rotating cylinder or Tipler cylinder. The idea is that a massive and long enough cylinder spinning at near the speed of light could theoretically create a frame-dragging effect, warping the space-time around it and allowing for time travel into the past. However, much like wormholes, these theoretical time machines come with their own set of issues. For instance, to build a Tipler cylinder, one would need an infinite amount of energy and a cylinder of infinite length. Not exactly practical. While these concepts are still theoretical, they show that time travel to the past could be within the realm of possibility. If time travel is possible, it opens up a world of paradoxes. Let's delve into some of the most renowned ones, such as the grandfather paradox and the bootstrap paradox. The grandfather paradox theorizes that if a person were to travel back in time and accidentally cause their grandfather's premature demise, they would never be born and thus couldn't have traveled back in time in the first place. A mind-bending cycle, isn't it? On the other hand, the bootstrap paradox involves an object or piece of information sent back in time becoming trapped in an infinite cause and effect loop. Consider a book sent back to its author before they wrote it. Who then really wrote the book? These paradoxes present significant challenges to the concept of time travel, creating logical inconsistencies that are hard to resolve. These paradoxes remind us that while time travel is a fascinating concept, it also comes with its own set of complexities. So where does this leave us on our journey through time? We've traversed the winding path of temporal understanding, starting with the fundamental concept of time itself. Remember, it's not just a tick-tock on a clock, but a dimension, a fabric woven into the universe's very structure. Then we delved into the groundbreaking ideas of Einstein, whose theory of relativity turned our notions of time and space on their heads. Time is not absolute, but relative, influenced by speed and gravity. Next, we ventured into the realm of the extraordinary, wormholes and time machines. Though they exist mainly in the realm of theoretical physics and science fiction now, who knows what the future might hold? And lastly, we grappled with the paradoxes of time travel. If we could journey to the past, could we change our present, or is the timeline immutable? While time travel remains a tantalizing concept, it's clear that we still have a lot to learn about the mysteries of time and space.